Let me show you one more, which is again quite independent of these other ones. If your people don't know binary, I wrote some binary games here. They can practice them here. It runs in your browser. So for example, if you want to learn nibbles, which is, and what I did was I taught Cisco for years. And in Cisco, you have to do this thing called subnetting, which involves really understanding binary. And a lot of my students failed to learn binary. So I changed to a new technique of teaching binary, which is each day I would do one of these things and then wait until the next day to do the next one. So you learn one thing at a time. So in base 10, you have 10 digits. And to write 147, it's 1 times 100 and 4 times 10 and 7 times 1. Hey, I see you're back, Michael. I'm glad you use them. Anyway, so this is how base 10 works. And base 2, so here's base 10. You have the hundreds place, the tens place, and the ones place, and we're all used to that. So base 2 is the same thing. You only have 2 symbols, 0 and 1. So if you write 1, 1, this is the number of 2s, and this is the number of 1s. 1 times 2 to the 1 plus 2 to the 0. So if you have a 3-digit number in base 2, it's the 1s here, the 2s here, and the 4s there. So 101 is 5. It's a 4 plus a 1 and no 2. And so you can count to 7. 0 to 7, here it is in base 2. 1 is 1, 2 is 1, 0, because you have a 2 and no 1s. 3 is a 2 and a 1. 4 is 1, 4 and nothing else. And 7 is a 4 plus a 2 plus a 1. And the simplest object to make is a nibble with 4 bits, half of a byte. And all you have is 1s, 2s, 4s, and 8s. So there are only 16 of them, and there's all of them. From 0 to 15, all 1s is 15 because it's 8 plus 4 plus 2 plus 1. And 10 is 10, 10 because it's 8 plus 2, but there are no 4s or 1s, and so on. So that's nibbles. And I made a little game you can play to prove that you know your nibbles, sort of based on the same logic as the Khan Academy. You have to get, I think, 10 in a row right to get the flag. So 110 is 2 plus 4, that's 6. 111 is 7. 10, 11, that's 11, and so on. And if you get one wrong, it tells you you're wrong. And when you go back here, you're back to 0. So when you get 10 in a row, you'll get a flag. Now, another thing that's kind of fun. Yeah, I have a few other things down here. So you learn nibbles, bytes, and hexadecimal. And then I've got a few other things of interest to cryptography that are a little less common, like modular arithmetic. Let me talk about the first one of them, because that's a good concept in cryptography that this is often new to my students. The binary they already know, or they know somewhat, and they need more practice, but it's somewhat familiar territory for them. But modular arithmetic is not, and it's really important in cryptography, because if I have a message that includes letters, or say bytes, and then I encrypt it, I don't want 1 byte to encrypt into 2 bytes. So you work on a modulus. So here's Modulus 9. You work on a ring from 0 to 8, just like a clock, which would be Modulus 12. And so if you have 8 and you add 1, you're back to 0. And if you have 1 and you subtract 2, you're back to 8. The answer is always on the ring. So they call that modulus. So to make something Modulus 9, you divide it by 9 and keep only the remainder. So from 0 to 8, Modulus 9 doesn't change anything, but 9 mod 9 is 0. You divide it by 9, it's 1 9 plus 0 remainder, that's the remainder. 10 mod 9 is 1, and so on. 15 mod 9 is 6. So any number you want can be mapped onto this ring with the modulus operation. So as high as you go, the output is always going to be from 0 to 8. You can have negative numbers. If I'm at 0 and I go back 1, that's minus 1 mod 9, but it's 8. Minus 2 is 7, minus 3 is 6, and so on. So you can have addition and subtraction. You can have, all right. So you can also have an associative law. If I have 0 plus 1 mod 9, I can take 0 mod 9, which is 0, and 1 mod 9 and add them together. I can distribute the mod in there. So 8 plus 3 mod 9 is 11 mod 9. That's 2. But it's also 8 mod 9 plus 3 mod 9, which would be, again, 11 going back. Here, here's more of these. You can distribute it that way. And you can do it with subtraction. So if I have 16 minus 5 mod 9, that's going to be 11 mod 9. But I could also do the modulus separately. 16 mod 9 minus 5 mod 9. 16 mod 9 is 7. And 5 mod 9 is 5. So I can get to 2 this way also. So here's modulus 4. You only go from 0 to 3. So 5 mod 4 is 1. And 12 mod 4 is 0. And here's modulus 6. So again, if you understand the basics of modular arithmetic, there's some challenges here you can do. And the last one, which is where people usually get a little confused, is inverse modulus. So here, you're going to do now you can now do addition of modulus numbers and you can do subtraction. You could also do multiplication. So here's the original thing I had. I can go from 0 up to 18. I can do multiplication, 2 times 9, mod 9, where I have a 9 to go around, and then another time I go around. So it's going to be 0. You can also distribute it. You can do 2 mod 9 times 0 mod 9. That's 2 times 0. You can do 2 times 10 mod 9. 2 mod 9 times 10 mod 9. 2 mod 9 is 2. And 10 mod 9 is 1, so the answer is 2. You could also work it out this way. 0, you go up to 9, 10. Then you add another 10, which is once around, and one more. That gets you to 2. So you can do multiplication on a modular ring, which is fine. Now, so when I multiplied 2 times 9 mod 9, 2 times 10 mod 9, I got 2. Now, suppose I take 2 times 5 mod 9. That's 2 mod 9 times 5 mod 9. That's 10. That's 1. So that means 2 times 5 is 1. 5 is the multiplicative inverse of 2. So if you want to encrypt something on a ring, you can multiply it by a key, like 2, and then to decrypt it, you multiply it by the multiplicative inverse, 5. So if you take the doubled number, so I start with 0, and I multiply it by 2. That's not going to work. Start with 1. Anyway, what we just did back here, 2 times 9. 2 times 9 mod 9 will give you 0. 2 times 10 mod 9 will give you 2. Now, if I take 5 times that, it will turn back to 10. So the decryption is a second multiplication operation. This is where it gets a little bind bending, because there is no such thing as division on the ring. There's no way to get to a half or a third or anything you get by division. All you can do is multiply, but you can encrypt things by multiplying by the encryption key and decrypt that by multiplying it again by the decryption key. So here's modulus 9. Here's what you do is you multiply 6 times various numbers, and you'll find that if you multiply 6 on a mod 9, all you're ever going to get is 630, 630, 630. So 6 does not have any multiplicative inverse. There is nothing you can multiply 6 by that will give you 1. Not every value has a multiplicative inverse, but 7 does. If I just start multiplying 7 times 1, 7 times 2, 7 times 3, I will find that 7 times 4 mod 9 is 28. That's 27 plus 1, so it's 1. So 4 is the multiplicative inverse of 7 modulus 9. And this is very important if you get into RSA. This is how RSA works. So here's modulus 4. And let's just show modulus 4 going around. So anyway, that's the, again, there are some challenges here where you have to figure out inverse modulus, multiplicative inverses, and that prepares you for understanding RSA encryption that works this way. So anyway, those are fun lessons to learn basic binary operations.